Okay. Hello student, this is Ashikul Deep. I'm your TA for PY205. Today I'm going to talk about oscillations, particularly a mass spring system. Say you have a horizontal mass spring system like this, where this one-dimensional system can frictionlessly move along x-axis. Let your spring constant be k and the mass of the object be m. Then we can analyze the motion of this thing. Say you extend your spring up to some length, like this would be your initial extension. Let's call it x0, and then you release the system. So as a result, when you release the system, it will oscillate back and forth. So sometime the position will be some arbitrary x at some time t, but due to conservation of energy, the amplitude, the maximum displacement from the equilibrium point cannot exceed x0. So let's say at some time, t, you are at your mass is at position x from the equilibrium point at some time t. So now here is your mass m and the spring constant is k. So we can analyze the motion really easily using Newton's law. So if we apply Newton's law, we can say that acceleration of the object, of the mass, can be written as m multiplied by x double dot, where double dot denotes the second order time derivative of x with respect to time. So that, due to Newton's law, mx double dot, which is mass multiplied by acceleration, would be equal to the net applied force on the spring. Now net applied force on the mass, actually, sorry for the mistake. Now on the mass object, the object of mass m, the only force that is being applied is force due to the spring, which is from Hooke's law, can be written as negative kx. So we know the restoring force is proportional to the spring constant and proportional to the displacement from the equilibrium point. So at this force is trying to restore, this force applied by the spring on the mass is trying to restore the equilibrium, so there is a negative sign. So we have the equation of motion for mass spring system as mx double dot plus kx equals to 0. So this is the thing you solve to get the motion of this object. So if we solve analytically, we can have x at some time t would be equal to some initial position, say x0, cosine root k by m t plus some initial phase delta. So if you release without any velocity from at x0, your initial phase angle would be 0. So in that case, like delta equals to 0, so it gives you like x of t equals to x0 cos square root of k by m t. That's all. Okay, but instead of directly applying Newton's law, we can solve this kind of system, which are basically one-dimensional, using in another way is called the energy approach. So when you try to apply conservation of energy to solve the system, that's we call it energy approach. So let's analyze the same system a little bit differently. At time t, the displacement of the mass object m, object of mass m, from the equilibrium point is x. So the stored potential energy in the spring would be V equals to half k x squared. So obviously this x is changing over time, so the potential, the stored energy in the spring would be changing. And say at that same time the kinetic energy, say T, would be half m v square, where v is the instantaneous velocity of that mass m. So this can be written as half m x dot squared, like this. So due to the conservation of energy, this kinetic energy and the potential energy, when you add those two things, so T plus V would be a constant quantity, let's say E, which is a constant due to the conservation of energy. So if your kinetic energy reduces, your potential energy increases, and vice versa. So we can analyze this motion by this way as well. So let's write everything down explicitly. So you get half m x dot squared plus half k x squared equals to E, which is a constant quantity. Now what's the relation between position and the velocity? So to get that, we can simplify the expression a little bit. Let's simplify. To do that, let's consider dividing the whole equation by E, and by doing that you can write it like this: x dot squared divided by 2E by m plus x squared divided by 2E over k. Equals to 1. Now let's rename one of our variable. So here x dot is also a dynamical variable because it's the velocity that's changing over time. So we can write it as x dot equals to y, which is just a renaming. That we are talking about the same velocity variable but in terms of different name, with a different name. So we can write it as x squared divided by 2E by k plus y squared divided by 2E by m equals to 1. So from our algebra courses, we know that this is an equation of an ellipse. So if we plot y versus x, so velocity versus position, we'll have something like this. Where this intercept in y-axis, this is going to be square root of 2E by m, and this x-intercept is going to be square root of 2E by k, like that. So now what happens is, when you start with a maximum initial position, Let me draw it a little bit carefully. So this should be like this. Yeah. So if you release the mass from a maximum position, let's call it x naught, then your system starts to oscillate. So as the spring tries to squeeze it down, like try to go to back its equilibrium point, so your initial displacement starts to decrease. So the value of x is going down, but as a result your system is gaining kinetic energy because it's losing potential energy. So your y value goes up. So effectively this point moves along this curve like this, and so on. So from this and this whole cycle actually repeats. Like you release the system from x equals to x naught, then initial displacement starts to decrease, but the velocity starts to increase. Then velocity finally gets a maximum value with your x equals to 0, but then due to the inertia of the system, inertia of the mass, it actually passes this point and keeps its motion. So then again it starts to squeeze the spring system, and if effectively again it comes to a rest again, then it starts to come back. So if I draw the diagram around it, so it should look like this. In this part it should look like this. So say you released from here, released from this position, and this is your equilibrium, then actually it's going this way. So its displacement is being reduced, but the kinetic energy, so it's speeding up, kinetic energy is going upward. At that part let's draw the diagram. Here is the equilibrium point, but this object has passed the equilibrium point. So it comes to the equilibrium point at this point here actually. So then the object is still going in this direction, but its velocity is getting reduced. So as you can see, it's moving this way. So the value of y is getting reduced. So eventually at this point here it comes to rest momentarily, then again it starts to expand. So in this part what happens is, so if this point is your equilibrium point, then the object is probably here, and this time object is going this way. Again at this point it passes the equilibrium point. Due to inertia it crosses that, and it goes like the new position becomes like this. It passes the equilibrium, but still it's going like the displacement is increasing, and finally the displacement will be maximum, and it will come to a rest, and the cycle repeats. So this is what happens. Your potential energy is reduced, or actually it's spending its potential energy by gaining kinetic energy, and vice versa, and it's repeating the cycle. Okay, so what can be done with this expression actually? So this expression, this relation between position and velocity can be used to actually find the equation of motion itself, like x as a function of time. I think that's out of the scope of this lecture, so I'm not going to explain that, but I can give you a sketch that you can try at your free time, so you'll have some fun doing this. So basically what you want to do is, starting from here, this energy equation, you can write it like half m dx over dt whole squared plus half k x squared equals to e. So what you can do with this is you are trying to integrate, so integrate with respect to t and x, so you need to separate the variable. That's what you are going to do. So you just write down things a little bit differently. So write this way: half m dx over dt whole squared equals to e minus half k x squared. So then multiply this the whole thing by 2 and divide it by m, so you get dx over dt whole squared equals to e minus half kx squared multiplied by 2 by m. That's what you get. Now what you can do is you can take the square root and get like this thing, and you'll have like square root of 2 by m multiplied by e minus half kx squared, pardon me, half kx squared, like that. And then you're actually separated the whole thing, so you can write like this: 1 over square root of 2 by m e minus half kx squared dx equals to dt. And now if you integrate with the appropriate initial data, like at t equals to 0, you have a value of x as x naught, and at some t you have some x, then integrating this thing you will find the result like x equals to some constant a cos square root k by m plus delta. So it's a standard integral. Actually I'm going to write it differently. Instead of a, I'm going to write it as x naught. So this is what you are going to get. Try it at your free time by yourself and see what you can get, if you can get this result or not. So this result actually tells a lot about the mass spring system. So number one, x naught, it tells you how much the initial position is, like what's the maximum amplitude of your system. So by your x naught you can actually calculate the maximum amount of energy or the total energy of your system just using this formula: E equals to half k x naught squared, because when x equals to x naught, velocity is going to be 0. So that's the amplitude. Now oh sorry, yeah, okay, so this is what you can get for delta equals to 0 case. Actually we are talking about delta equals to 0, so yeah, this is what you can find. And another is the frequency, like this cosine square root k by m multiplied by t, that the coefficient of t is your omega. So omega equals to square root k by m. That's your angular frequency of the spring. So you can write the same thing as twice pi f, where f is the ordinary frequency, not the angular one, and the ordinary frequency is related to the time period, like 1 over t equals to f. So I can write like this, where t is the period, time period. So we can actually find t out of this expression. So t equals to two pi root m by k. So using this formula, actually you can find a natural frequency of your mass spring system. So that's all for today, and see you next time. Goodbye.